Welcome back to another lecture. Today we're going to talk about horizontal alignment. Last week we talked about radius of the curvature, horizontal radius. If a vehicle is going less than 10 miles an hour, then we use a minimum turning radius using AASHTO, which there was a different template for different vehicle classification. And then if your vehicle went over 10 miles an hour, and then there was a formula, which you can see on the screen. We used that one, which is based on the speed and the cross slope of the roadway. Now we're going to talk about the horizontal alignment. When we look at the horizontal alignment, again, it's just very similar to vertical alignment. You have the tangent line, and then you have the intersection, then you have the curve. In vertical alignment, we wouldn't calculate the elevation. In horizontal alignment, we have to calculate the deflection angle. One thing you really want to focus on is what is the difference between a degree of arc or a degree of chord. So if you look at this right here, and this has been the radius, this will be the center of your radius. When they design highway or railroad, they always use a 100-foot arc or 100-foot chord. What I mean by that, if you look at up here, this dimension from here, and that's being like that, if we call that 100 foot, that will be arc. And you can also see it on the screen. And what does it mean? I mean, if this angle, we call this angle DA, D of arc, I mean at that angle, could be 2 degrees, 3 degrees, 4 degrees, that angle will give us 100 feet of arc. And highway usually uses 100 feet of arc, and they use a degree of arc. Now, if it was a railroad, they'd be using a chord, which is the chord will be right here. It will be this one. So if you make that DC, and 100 foot will be this distance, the straight line. And that's a degree of a chord. And that's the difference between chord and arc, as you can see on your screen here. Okay, I'm going to erase this because I need some space. And one of the things we look at it, so the radius to be calculated, whether it's a degree of arc or it's a degree of a chord, is different. And then the radius, so we're going to use here, it's going to be R for this one. Radius is going to be based on arc, which is a 5729.6, and divide that by degree of arc. Then there's another relationship in the formula you got to know is the length of the arc divided by deflection angle, same as the length divided by deflection angle, and then L2 divided by L1. If you look up on the screen, it explains which one of those are. And the delta is the intersection angle between these two. And also, this is your degree, hold the entire, this will be the degree that we're looking for, that we're given per curve itself. But also the other formula we have to look at, you can see on the screen, is how we're going to calculate the tangent, or how we're going to calculate the chord length and the length of the curve. So let's go ahead and do an example. And you can see the example on the screen. We have this curve, and it's a 4-degree curve, which is a 55 degree and 25 minutes. So this becomes to 55 degree and 25 minute. All right. So and then they're telling us the PC is at station 238 plus 44 plus 75. So PC is at station 238 plus 44 plus 75. Okay. And that's it. And we're going to go ahead and design this horizontal curve. What is the first thing we do? really the first thing we do, we're going to find the radius. So let's go ahead and calculate the radius. And the radius comes out to, based on this formula, r is equal 5729.6 divided by, and they said that it's a 4-degree curve, so dA is equal 4 degree. So divided by 4 degree, and that will give me 1432.4. Okay, so that's the first thing we do. Now we have that, we know this radius is equal to 1432.4. Next thing I want to find out the length of my curve from here, from PC to BD or AB. Remember, the length we're going to find is going to be this length. So the length is equal, again, looking at the formula, the length of the curve came out to be, I have to find that, put it on the screen, is R L equal R radius time delta time pi, and divide that by 180. Okay, one thing you got to do before we get there, we got to find out what is delta in terms of angle, not because we have it in 55 degree and 25 minute. Let's convert 25 minute to degree. That means if 1 degree, right? Let's do a simple calculation. If 1 degree is equal 60 minute, then 25 minute is equal how much? So it'll be 25 times 1 divided by 60. That comes out to 25 divided by 60.417. Am I right? Close enough. So that's going to become 55.417. Now we're going to come in here. We have everything and we need to calculate. So our L is equal to R, which was 1432.4, multiplied by the angle was 55.417, multiply that by 3.14, and divide the whole thing by 180. Normally I put all these in Excel, so I don't have to worry about the rounding. And that comes out to 1385.42. 1385.42. Okay, so that's the length of our curve. Now we have that. The next step is, okay, when we look at that picture up on the screen, we're going to find the individual angle. So after that we're going to go ahead and find delta 1. And based on that, but we're going to find L1. To find L1, we're going to find out where our next station is. So the station is 238 plus 44 plus 50. Our next station is going to be, say it's going to be right here. And that's going to be 239. So we got 239 right there. Then what's the difference between 239 and 238 plus 44 plus 50? 44 plus 75. We did talk about that in class. Instead of writing 239, so need some room here. Say 239 plus 00 minus 238 plus 44.75. All right, so I can go ahead and say, you know what, instead of writing 239 plus 00, why not just say that's the same as, so 239 is same as 238 plus 100, same thing. Now you have that, and then you have 100 minus 44 plus 75. So it comes out to 55.25. So that will give me the L, which is right here, this distance right here, okay? Now I got L. Now, you got something when looking at this curve, don't look at the picture, because this is kind of exaggerated. Because this degree of 4, the curve is so wide, and the angles are so small, if I had to draw that per scale, you probably wouldn't see these two lines if you're on top of each other, just about. So we know our L1 is 55.25. So what I'm going to do next, I'm going to use the formula above right there. And because now I have L1, I have L, I have delta, I don't have delta 1. I can calculate delta 1 from there. And my L1 is going to be, so let's write this down. L1 delta 1 is same as L divided by delta. That's a big L. We did calculate L. And that equal L1, it came out to 55.25. Divide that by delta 1, which we don't know. And that's equal 1385.2.42. 0.42 divided by delta, which was 55.417. So delta 1 comes out to calculating, I got 2.2 degree. 2.21 degree. All right, good. So we got set right there. We found all that we want. Now we found delta 1, that's our deflection angle. So when we sight from here to here, and we want to know where this station is going to be, how much angle we're going to, sight from here to there, and how much we're going to come back on a degree to meet this line here. And that's going to be the chord. So find the chord. So we got to look at the equation for the chord. I don't think I got them on board. Okay, so C1, which is on this side, it's going to be equal 2R sine of delta 1 divided by 2. Am I correct? Yeah. And that's going to come out to 2 times R was 1432.4 times sine of 2.21 divided by 2. Okay, and that gives me 55.25. How do you like that? Okay. So basically saying that these two lines are equal. Why? Because the angle, the deflection angle, this angle right here is so small. It's 2.21 divided by 2. And that's how we can say they're so close. All right, we found this one, delta 1. But again, take a look at the picture on the other side. We found delta 1. Now we're going to find delta 2 on the other end. Before we do that, we've got to find station B. What's the station B? If I know station Y is 238 plus 44.75, and I need room. Okay, don't go away, I'll be back. Let me erase this. So station 238 plus 44.75, add that to the length of the curve, which is from A to B, which was, the length was 1385, plus station 13 plus 85.42, and that comes out to, I think I have it, 252. What do I have here? I got it. 252, 30.7. 252 plus 30.17. If you have a hard time, you add this to this, it becomes 130.7. So take 100 out, put it on this side. to make it 252.317. So I get two. If I look at the Excel spreadsheet and you need all these stationing, so this station is 252 plus 30.17. Okay. Now what do I do from there? To find my delta 1, I gotta go to the next whole number station. So is this 52 plus change? The next station is going to be 252. That's what I'm looking for. I'm looking for station 252. 252 plus 0, 0. And therefore, what's the difference between those two is a 30.17. And if I say that's a 30.17, that means my L2 is equal 30.17. So now once I have that, I do the same exactly thing I did on this side. All right. Okay, let's erase this stuff here. Okay. Okay, so we're gonna say, let's make that to L2 delta 2, and this become L2. So L was 1385.42. 1385.42 divided by delta 2 is equal L. Our L was, I shouldn't erase that. No, what am I doing here? Okay, L2 is 30.17. 30.17. Now I got 1385.42. Divide that by delta, which was 55.417. And that gave me delta 2 is equal 1.2 degree. Okay. Now I have that. Then the next line I'm going to do, let's stay with the pink anyway. We want to find C2. Okay, C2 is 2R, it's 2 times R. R was 14.4 right here. And time sine of 1.2 divided by 2. And that gives me C2 is equal, what do I have for C2? 30.17. Okay, so 30.17, that's the same as yeah, same as what I had there before. Okay, so the angles are so close. Now we have that, so we found everything. We had this right here. We had our horizontal curve, and we knew the deflection angle up here. We know the station in here, and then we continued, and we know the degree, which was degree 4. The first thing we did, we went go ahead and calculate the radius, and then we calculate the length of the curve. So once we knew those two, we used this relationship over here to calculate the L1 on this end and L1 on that end. The L1 is when you have a station here, and if your station is not on a whole number, then you have to go to the next station. That's the difference between those two, and that's what we did on both ends. Once we did that, and now everything is easy. Everything is 100 foot, station, 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 and it can fall in line, just like we have on a spread Excel sheet. So let's go ahead and calculate one full station. And I don't need to know the L, because L is L3 or L4 or L5, it's all 100. So all I need to calculate is, the CD. And CD, let's make a room here to make CD. All right. So I'm going to calculate CD, which is equal, if you put them back on the screen right here, you can see 2r sine d divided by 2, and that's a d arc, so which is equal 2 times, which was the radius right there, 1432.4 times d divided by 2 is 4. 4 divided by 2. And that gave me CD is equal, what do I have? 9898. Okay? And you can calculate the deflection angle from there on. If you take a look at the spread Excel sheet, so now we're coming in to the first station, and our deflection angle was what? Our deflection angle, which is it brings it back to the curve. You can go either from here to here or from there back to there. It's delta 1 divided by half for the first station. And the next station is going to be delta 1 divided by half plus d1 divided by half. And the next station is combination of this two plus d1 divided by half. And the next station is combination of all these angle plus d1 plus divided by half. So when you go into Excel, you just take that cell and plus d divided by 2, and you drag them all the way down until you get to the other end. Once you have your deflection angle, you have your length, you can lay out your curve.